So we discussed the properties of entropy in the previous class. So today we will continue along that direction and we will define the conditions for spontaneity and equilibrium. Now remember that whenever I write ds or any differential change in entropy, from now onward we will consider this ds to be equal to the ds of the system only. We are not considering the ds of the universe. The reason is, when you do an experiment, the focus is on the system, not on the surrounding. We do some experiment in the surrounding so that we make some changes in the system and we observe the system as we make those changes. Now also remember that for a reversible process, we will have d cross q by t is nothing but d cross q reversible by t. But if the process is irreversible, then the d cross q by t associated with the system is actually less than d cross q reversible by t. So by definition, entropy, ds, or differential change in entropy, which is defined as the reversible heat change, dq reversible by t, must be greater than or equal to d cross q by t. Now when I say d cross q, it is the differential heat change associated with the process. If it is reversible, then d cross q by t is nothing but d cross q reversible by t. So that is equivalent to entropy. However, if it is irreversible, then d cross q by t is not equivalent to d cross q reversible by t. And what it means, we discussed that the reversible heat change between say state 1 and state 2 can be brought in by many methods, and if we consider an irreversible path, which is suppose this path, then the associated heat change is not equivalent to the reversible heat change. So when we consider entropy, we have to consider an reversible path which is associated between these two states. So always keep that in mind, that d cross ds is actually d cross q reversible by t. Now this we proved starting from a discussion of how basically we had a irreversible path, and then if you remember from the previous class that we considered a cyclic process which was just kind of reverse of our Carnot cycle, and then from the argument we showed that this will always hold, that ds is always greater than equal to d cross q by t. And again remember that we are now only talking about ds system, because even if I don't write it, the ds will always mean that we are only looking at or observing the system. Now the question is, as I said, that we have a irreversible path which I have drawn here as a dotted line, and then we have to consider a equivalent reversible path which is here, but there could be many reversible paths. Let us try to understand this. But what it means is that for any reversible path, the value of d cross q reversible by t has to be equal, because otherwise we'll have a inconsistency in the definition of entropy. So once again we are showing most of the things in the pressure volume diagram. Suppose I have a reversible path which is say going from here to here, say state 1 to state 2. Now or better actually consider this path which is state 1 to 2. And then let us call this process as process 1, and also imagine that we took QH amount of heat during this transformation, and this is typically an isothermal reversible transformation. Now the question is, there could be other reversible paths, as we just argued. What could be the other reversible path? Going from the same initial state, which is state 1, to the same final state, which is the state 2. Now you can consider another path which is like this. This path is also reversible because there is a reversible adiabat. Then there is a reversible isotherm, and again we will have a reversible adiabat. So this entire path, which is just like this, let us denote it as path 2. So basically we said, going from 1 to 2, we have either a path like this, which we called as path 1, or there is a path which is like this, which is also reversible, but it consists of 3 different sub steps, but that is also a reversible path. So the question is, are the heat changes similar? It has to be, because by definition the delta S, or the finite change in entropy, which actually we can get by going from a finite change in the integrating over a finite path, that will be nothing but S2 minus S1. So whatever path we take, as long as it is reversible, the associated heat will be dq reversible by T, and since entropy is a state function which does not depend on path, the associated heat change should be equivalent. Now you can easily figure that out because we already discussed it in slightly different argument we provided when we were discussing the Carnot cycle. Now you remember that for the path 1, if you calculate this quantity delta S, which will be nothing but QH at say TH, suppose the temperature was TH, and again just think about that the temperature for the sink or the heat sink was TC. Now see here that we are doing a reversible expansion here. So unlike Carnot cycle, there will be a heat absorption. Suppose this is QC. Now for the second step, then delta S2, which has actually 3 sub-steps. So the first sub-step is adiabat. So the entropy change will be 0 because heat change is 0. Second one is heat withdrawn from the surrounding is QC. That will be divided by TC, and then we'll have again 0. So together we are having something like QC divided by TC. Now we can always construct a cyclic process where we can say that the delta S1, and then if we consider the reverse of delta S2, which will make again the entire process as a cyclic process. So then we can always argue that this step has to be 0 because entropy is a state function, and for any cyclic process, for any state function, the value of the at the end of the cyclic process, the state actually is regained, so which means the associated change of that particular quantity will be 0, just like internal energy or entropy. So we can always argue that we'll have QH by TH minus QC by TC, which is equal to 0. Now there is no surprise that we got it because we already considered the Carnot cycle and similar expressions also appeared there. But the logic we are discussing right now is slightly different. So what we got just now is the entropy change for the first step is exactly equal to the entropy change in the second path. So path 1 or path 2, as long as we consider the reversible path, it doesn't matter which reversible path you choose. So in a nutshell, what we just said is that we have two states, state 1 and state 2, and if you consider an irreversible path and ask this question, what is this entropy change, you have to consider a reversible path. Which reversible path, it doesn't matter, because as long as it is reversible, all the d cos q reversible by t for all this family of paths will be same, and you have to take that value to define entropy. However, the heat change associated with this path will always be less than d cross q reversible by t, but that quantity dq by t, d cross q by t is not necessarily entropy. If it is reversible, it is equal to entropy. If it is irreversible, it is not equal to entropy. Now let us move on and then try to understand what are the possibilities or conditions for spontaneity, or conditions for having a spontaneous process. Now, spontaneous process means actually it is just spontaneous. It happens all by itself. So there is no driving force required for that. Now, all spontaneous processes, which means must be irreversible in nature, which we discussed that by irreversibility we mean there is an arrow of time. So at an earlier time the system was in some state, and then the system is evolving as the time progresses to a new state. And then this is irreversible in the sense that it cannot be reversed back, because it is and it happens spontaneously. So spontaneous process by definition is an irreversible process. Now let us understand what are the conditions for spontaneity. We already have it, that this ds, remember it's the ds of the system, must be greater than or equal to d cross q by t. Now we can rewrite it. We already wrote it in different fashion. Like you can write it in TDS is greater than or equal to d cross q. So the greater than sign means it is a spontaneous process, and equal to means it is under equilibrium, which means it's a reversible process when the system is in equilibrium. Now you can write that d cross q as du plus d cross w as before, and we showed that if you write it in that way, TDS will be nothing but, remember that from the first law, du is d cross q plus d cross w. So d cross q is nothing but du minus d cross w. So we see that we can actually, for a reversible process, also further write the work as a pressure volume work, and we can write it as a PdV for any process, not only reversible, or P opposing dV. Now notice here that the way we are writing is, if I move the du on the left hand side, we'll have du is less than or equal to TdS minus PdV. Now if you remember, we wrote a series of equations. There are total 4 equations, one for U, one for H, enthalpy, one was for A, Helmholtz energy, and one was for G, which is Gibbs energy, and we wrote equal sign. All these energies, when we write it in terms of equal sign, that means actually these are the conditions of equilibrium. And similarly, you can have the conditions for spontaneity, where we'll write it as the less than sign. So this is basically the condition for spontaneity and equilibrium written together. So all these equations will be slightly modified in the sense that you will have du is less than or equal to TdS minus PdV. So all the equal sign you can discover later how it comes. So you have to just follow from this fundamental equation, and then you can build up all other equations as we showed in the last class. And dH will be nothing but TdS plus VdP. Similarly, dA will be nothing but minus SdT minus PdV, and dG will be nothing but minus SdT plus VdP. So yesterday we wrote everything as equal sign, which is stands for equilibrium, and today this greater than sign stands for the spontaneous process. So I'm just writing it together, the condition for spontaneity and equilibrium. Now we'll examine one by one. Particularly we'll start with this one, but we'll see that the most important equation which is very important for chemists is perhaps the equation for the Gibbs free energy, and we'll have a slightly more discussion on the Gibbs free energy. Now let us start with the equation for du. Now as we see that what we have is, for the condition of spontaneity, is du is less than equal to TdS minus PdV. Now consider heating at constant volume. So when you heat a substance, whichever substance it is, be it gas, liquid, or some solid, so what are the conditions that will happen that will make the system or the transformation spontaneous? Of course, we know that the temperature of the system will increase. Now, if we consider constant volume and I am supplying heat, so the condition can be further reduced. Since the volume is constant, dV will be 0. So this is the condition. Now think about it. What is ds? ds, we already know that this is basically the change in entropy. Now think about one step further. If we have not only constant volume, we have also imposing that the internal energy is constant. So if we make this condition energy, or better to write it as internal energy, is constant, so then we'll have the condition that du is 0, which means the condition for spontaneity will be ds greater than equal to 0, or ds is greater than equal to 0 because temperature is constant for constant u, because we already made two constraints. One is energy is constant, and we had earlier made another constraint that volume is also constant. So this is one of the equations for or conditions for spontaneity when both the energy and the volume are kept fixed. Similarly, you can also argue that if I kept the entropy fixed, entropy is constant, then this term is 0, then the condition will be du is less than equal to 0. Under what condition? Constant entropy and constant volume. So we will see that similar equations will be very necessary where we are keeping the internal energy constant and volume constant. Now this will be the conditions for this particular two constraint, constant volume and energy, but usually when you make a transformation, you do not keep the internal energy or volume constant. Suppose we are doing a transformation at constant pressure and temperature. So this is an usual condition for chemists. Like when you, for example, boil water and you keep the temperature constant because it is suppose being heated at 100 degrees centigrade and the temperature does not change as long as water vaporizes, and suppose we are doing it at 1 atmosphere, so the pressure is also not changing. So we have to make a condition of some quantity, we do not know it yet, which will be greater than or less than 0, and we need to find out these conditions at constant pressure temperature, how the system behaves. Now we have to define this quantity, and we'll figure out that actually the conditions will be given by the Gibbs free energy at constant pressure and temperature should be equal to less than 0. That will be the condition for spontaneity. So what I'm trying to say here is that the internal energy keeping it fixed and volume keeping it fixed is not a natural choice for experiment. Whenever you do experiments, probably pressure and temperature are the two conditions that you can keep constant. But then if you keep pressure and temperature constant, ds greater than equal to 0 is not a condition for spontaneity and equilibrium. You have to have some other equation that we'll discuss. And we'll discover that Gibbs free energy is the condition. Now, just like we had ds and du for constant energy and volume and constant entropy and volume, we can also start with the equation for dH in the similar way like we started with the equation for du, and let's see what we get out of it. So if you start with the dH equation, let us consider as before that we are heating a substance at constant pressure. Now we started with the equation that du is d cross q minus p dv, and we made the constant volume process to make this 0, but we could have just directly argued that at constant volume d cross q at constant volume is nothing but du. We already discussed it when we discussed the processes like du is cv dt plus del u del vt dv. When we discussed all those nice mathematical formulation, we discussed this one. Similarly, we know that if a constant pressure process happens, the d cross q at constant pressure is nothing but enthalpy. You can actually test it by using the same equation, and then in the enthalpy equation dH you have a v dp term, and you are just making the dp to be 0. So that is the condition, but we are just making a direct argument here. Now what it means is that we have the same condition that TdS must be greater than equal to dH for a spontaneous or equilibrium process written together. So what we have, again as before, we can make the one constant same. Say for example we are saying that at constant entropy what happens, or before that maybe we can first ask at constant enthalpy what happens. As before, you can discover that for constant enthalpy as well as constant pressure, because we have made two constants, one is constant enthalpy, the other one is constant pressure. So what we see here is that if we make those two conditions together, so the spontaneity or equilibrium is given by this equation. And as before, if we make it as or do the transformation at constant entropy, then the condition for spontaneity and equilibrium are given by dH less than equal to 0, where the transformation were happening at constant entropy and pressure. Now let us try to understand what does these quantities mean physically. Now let us go back one step. We first said that this is a condition for equilibrium at constant energy and volume. Now this is not surprising. Suppose you are heating a process, you are heating a substance in the process, and you are doing this transformation at constant volume. What does it mean? So if you keep the volume constant and if you supply heat, the temperature of the system will increase, of course. And if you keep the internal energy also fixed, then the entropy of the system must increase. So there is no surprising. Now this one, when the entropy is constant, and then we see that the du is less than equal to 0 is the condition. Now for a spontaneous process, it means that the internal energy dropping down is a spontaneous process, which does not really make sense. Now the explanation for this is just like that. You are heating a substance and then you are not allowing the entropy of the system to drop down. Then you know that the condition, the global condition for the spontaneity is delta S system must be greater than 0. So if the system's entropy is constant, this for the global entropy, we have the delta S universe must be greater than equal to 0. If we keep the system's entropy constant, that means the surroundings entropy must be greater than 0. And in order to make the surrounding entropy more, the system should supply energy to the surrounding, which means the energy of the system should drop down. So that is the meaning of this process. Similarly, if you ask this question, if I have a constant enthalpy process at a constant pressure, it is not surprising that the spontaneity is given by ds greater than 0. The entropy of the system must increase. And similarly, if we keep the entropy of the system constant and ask about the spontaneity, then the surrounding entropy must increase. Then heat should flow from the system to the surrounding at constant pressure, which is nothing but the enthalpy, and the enthalpy of the system should decrease. Now let us consider the two other situations where we have to write something based on the Helmholtz energy and the Gibbs energy. And if you look at the equations for Helmholtz energy and Gibbs energy, the natural condition for the first one, which is the Helmholtz free energy, is that we have to keep the volume constant. Now if you consider a constant volume process, then we naturally see that the condition for spontaneity and equilibrium written together is this, or du minus tds is less than equal to 0. Or now if you remember that A, or the Helmholtz energy, was defined as u minus ds, so we can just write at say constant temperature, or basically here we'll have dA is nothing but du minus tds minus s dt. Now we can make this term to be 0 at constant temperature. So this term du minus tds is nothing but dA. So you can write that dA is less than equal to 0 if the process happens at constant volume and constant temperature. Now constant volume and temperature are two natural choices. So in many cases we'll keep the volume to be constant and then keep the temperature also constant, and suppose we can heat up a system or do something else where the relevant quantity to look at for spontaneity will be dA. Just keep that in mind. And similarly, we could also get another equation for constant pressure process, where we can actually right away use this other equation where we wrote that constant pressure means, remember, it will be greater or equal to dH, because QP is nothing but, or D cross QP is nothing but dH, and then dH minus TdS is less than or equal to 0. Now, as before, we can write G as H minus Ts. That was the definition of Gibbs free energy, which will give us dG is nothing but dH minus TdS minus SdT, following the chain rule. Again, we can make this term to be 0. So we are further assuming at constant temperature, this term is 0. So dH minus TdS, this term, which is dG, is less than or equal to 0 for constant pressure and temperature. So these two equations, one is dA is less than or equal to 0, dA at constant volume temperature less than or equal to 0, and dG at constant pressure temperature less than or equal to 0 are more natural choices for describing spontaneity. Now, if you try to remember all these things, if you go back one step and remember that we had all these four equations. Now, the conditions for spontaneity, if you want to impose, if you use the first equation, remember that I have to keep ds constant and dv constant, then only I'll get du less than or equal to 0. It directly follows from this equation. Similarly, for dH less than or equal to 0, I have to keep ds and dp constant. But usually those are not natural choice that you vary in experiment. Natural choices in experiment are pressure, temperature, volume. That those you can keep constant. You can either keep temperature and pressure constant, or you can keep temperature and volume to be constant. If you keep the temperature and volume to be constant, then your condition is dA is less than or equal to 0. And if you keep the temperature and pressure to be constant, then your condition for spontaneity is dG less than or equal to 0. When I say less than or equal to and say spontaneity, it means that it is spontaneity and equilibrium together. If you consider only spontaneity, it will be less than. So now we have two useful relations. One is dA at constant volume and temperature less than or equal to 0, and the other one is dG at constant pressure and temperature should be equal to 0. So whenever we are considering, or whenever we will consider constant volume temperature process, we'll look at what is the associated change in Helmholtz free energy. Whenever we look at a constant pressure temperature process, we'll look at what is the associated change in Gibbs free energy. Now, let us move on and try to understand what this Gibbs free energy and Helmholtz free energy is all about. Now, to understand that, let us try to understand first what is dA, what is the physical significance of dA, what does it mean. Now, you can easily get a very nice equation for that. We can again start from du is less than TdS minus PdV. But instead of writing it PdV, you can always write it as the original equation, which was TdS plus d cross W, where d cross W is some kind of work, and we know what is this work. It's a pressure volume work. So we could write the d cross W as greater than or equal to du minus TdS, but we know that this du minus TdS is nothing but dA at constant volume and temperature. And of course, this will be applicable for any change, but we'll consider only the equality sign right now, because we are just considering the maximum or minimum amount of work. Now look at this equation. What does it mean? So we wrote that d cross W, which is the work done, is greater than or equal to the change in Helmholtz free energy at constant volume temperature. Now, what it exactly means is that I can have some work done, and by definition, the work done means here the work done by the system will be negative and the work done by the surrounding will be positive. So if the work done can be, it is saying this equation that the magnitude of the work done can be equal to dA, or it can be more. So what it means is that the minimum amount of work that we can get is dA. Now what is the minimum amount of work? Minimum amount of work means this change. Now we have to consider the work done by the system, because remember, for system it's a negative work if the system works. So if the system works in a maximum way, D cross W will be minimum because it's a negative work. If the surrounding does maximum work, so then D cross W will be maximum. So from system perspective, this is equivalent to maximum work done by the system, and this is nothing but the maximum work done by the surroundings. So since from this equation we get the minimum value of D cross W, we can argue that this D cross W is nothing but, or if I write it in the other way, that this dA at constant volume temperature will be equivalent to the maximum work done by the system. So what we just discovered, that this Helmholtz free energy, or the differential change in the Helmholtz free energy, is equivalent to the work done by the differential work done by the system, or the maximum differential work done by the system. We could also use just remove the differential notation, and we could just write that this Helmholtz free energy is nothing but the maximum work done by the system. Remember, it is always we are saying that it is by the system. So similarly, you can figure out that this other differential, which is dg, just like here we had the maximum work done, but remember this work is what kind of work? It is the pressure volume work, because instead of minus PdV we wrote D cross W. But there could be other non-PV work which is known as non-pressure volume work. For example, suppose electrons are flowing in a circuit, so that will cause electricity, and that involves a finite amount of work. So that work will be the non-pressure volume work, and you can write this D cross W as some PDV term, which is always negative PDV because of our convention, plus some additional work, which I am writing as D cross W additional, and then you can easily show if you just write the total work done as like this, and if you start from the same equation which you started with, du is TdS plus D cross W, and use the fact that H is G minus Ts and write it in terms of the differential notation, then you will discover that this dg at constant pressure temperature, remember that when you write as A, the natural choices are constant volume temperature, but when you write anything in terms of, say, the Gibbs free energy, the natural choices are constant pressure temperature, and that will be nothing but the maximum additional work done by the system. So that is kind of a physical interpretation that we have, that the Gibbs free energy corresponds to the maximum additional work or the non-PV work that the system can do. So again, I'll refine my statement. The maximum non-PV work done by the system will be equivalent to the Gibbs free energy at constant pressure temperature, because this is very important. Similarly, the maximum PV work which is done by the system can be related to the Helmholtz free energy at constant volume and temperature. Now, usually when you, this notation stands for, we have to use a delta sign here because we are considering a finite chain, and we do not use any delta sign here because it's an inexact differential. Similarly, we can use actually a delta G sign here because it's also an exact differential. Now, why it is exact and inexact differential, you can easily figure that out because we wrote that they are all connected to du and dh, which were actually all exact differentials. And similarly, you can also argue from the connection of du and dh that dA and dg are also exact differentials.